Alright, it has been quite some time since I have had to record a new video, so there may be some technical difficulties as I kind of remember what I'm doing here. But anyways, we'll jump right into it. So in our last class in person, we introduced ourselves to the idea of kinetics, right? Studying the rate at which reactions occur, okay? And we talked a little bit, generally about what are some of the factors that can influence rate. The two things that we sort of landed on were temperature. So generally speaking, higher temperatures means that particles are moving faster. They collide with more energy. There's more thermal energy available to break the bonds of the reactants and overcome that activation energy, right? So generally speaking, increases in temperature tend to increase rates of reaction. Also, having more reactant present and having those reactant molecules, or whatever they may be, having them collide more often, so just having more of them there tends to increase reaction rates as well. So increased concentration of reactants tends to lead to, generally speaking, increased rates of reaction. Okay? So, that was all sort of introductory. What we're going to get into first, in terms of specifics, is something called the rate law. Okay? So what all this is an equation that describes the rate of the reaction. Okay, so it's a mathematical thing. Okay, and this is the general form of a rate law. Okay, and this is for this reaction. Okay, so we've got two NO2 molecules decomposing into two NO molecules plus an oxygen gas molecule. Okay, so this is the only reactant. Okay. And so, generally speaking, rate laws look like this. They are some sort of rate constant multiplied by the concentration of the reactant raised to some power n. Okay? K is this rate constant. Okay? It has different units depending on the form of the rate law. We're going to get into that in a second. K is usually temperature dependent, and it can be, it depends on the reaction. So it's going to be a different value for different chemical reactions. Okay, so like it's going to be you're going to have a different K value for this reaction compared to some other reaction, and for the same reaction, K is going to be different depending on what temperature you're at. Okay, and that makes sense, right? Because like we said before, if the temperature changes, then the rate is going to change. Okay, and so that's reflected, in K. Now, well, I don't want to say most, but a lot of reactions, the speed or the rate of the reaction does depend on the concentration of the reactant or reactants. Okay? Not every reaction depends on the concentration of the reactants, but a lot of them do. Okay? The degree to which the concentration of the reactant matters is called the order. Okay, so that's this exponent here, this value of n. Okay, and you'll see here it says essentially how large or small n is communicates to us how strongly the rate depends on the concentration of that reactant. Okay, now here is where things are going to get a little bit fancy. Oh, you see, I knew I was going to have some technical difficulties here, so hold on a second. Let me, oh boy. So yeah, I have to be in like a Zoom call here to use the little drawing tool. Okay. Let me give this a try here. Here we go. Okay, cool. All right. So let's say that n is equal to 0. Okay, so let's say that n is equal to 0. That means that the rate would be equal to K times the concentration of NO2 to the 0th power. Anything to the 0th power is 1. So this part of the equation then would evaluate to 1, okay? Which means that the rate is just equal to k, okay? The rate constant. This is called a 0th order reaction, okay? 0th order, okay? These reactions, what this means is that the rate does not depend on the concentration of the reactants, okay? It's literally just temperature dependent, okay? It's just the rate constant, which changes as a function of temperature, okay? So, you know, it is what it is, right? There are some 0th order reactions, okay? There are, however, lots of reactions that are not 0th order, okay? They do depend on the rate, okay? Let's look at this. Let's say n is equal to 1, okay? This is called first order, by the way, okay? This would be NO2 to the power of 1, okay? We typically don't write things when they are to the power of 1, all right? So you typically won't see that. So this right here would be the rate law for a first order reaction, if this reaction happened to be first order, okay? So the concentration of the reactant at any given time does matter, okay? It does influence the rate. You've got more higher concentration, then the rate's going to be higher, right? If the concentration goes down, then the rate is going to go down as well, okay? It's going to start to slow down as the reactant is consumed, okay? Then we also have a third possibility here, which is that n is equal to 2. Okay, this is called a second order reaction. Okay, and so the form of the rate law here would be, you guessed it, NO2 squared. Okay. What this means is that the rate of the reaction is strongly influenced by the concentration of the reactant. Okay. Now, this reaction specifically that we're looking at here, right, NO2 decomposing into NO and O2, it's not like it can be all three, okay? Each reaction is going to be either 0th order, first order, or second order, okay? And that's actually with respect to each of the individual reactants. This reaction only has one reactant, okay? So we're only talking about, you know, its order with respect to the one reactant. If you had several reactants, so let's say you had A plus B turns into C, okay, the general form of the rate law for this thing would be K, and then the concentration of A to some power of N. N would be the order of the reaction with respect to A. But then you would also have to factor in, potentially, the concentration of B, okay? And this is going to have a different order. That would be M, okay? So, you know, there are situations where you could say, okay, maybe this reaction is 0th order with respect to A, so the concentration of A does not influence the rate at all, but it is first order with respect to B, okay? So the concentration of this matters, but the concentration of A does not matter. It does not influence the rate. Or it could be the other way around, right? Or they could both be 1, or they could both be 2, okay? So it just depends, right? Each reaction is going to be, each reaction is going to be a little bit different, okay? Okay, so that information is summarized somewhat on this slide right here, okay? And so in AP Chem, these are really the only three scenarios that we're going to look at, all right? When n equals 0, n equals 1, or n equals 2, okay? N can also be some other values, okay? It can actually be fractional, okay? But in AP Chemistry, we're not really, that's not really in the scope of the course or the exam, okay? All right. Now, for the remainder of this video, I'm going to be talking about the units of K, okay? So that rate constant, and this is going to enable you to finish the final couple of problems in part 1 of the problem set. So the 5.1, 5.2 problem set, there's part 1 and part 2. The last couple of problems in part 1, as of this moment, you are not really equipped to be able to handle that. Once I talk a little bit here about the units of K, then that should get a bit better for you, a little bit easier for you. Okay, you'll be equipped to handle those questions. All right, I'm gonna share a whiteboard here. Okay, hopefully the screen is not blinding you at this point like it is me. All right, let's talk about just a generic reaction. Okay, so super generic, and let's say we have A turning into B plus C. Okay. Let's say that the reaction is 0th order with respect to A. Okay, so the rate the rate of the reaction is not influenced by the concentration of A, meaning it does not matter how much A there is, the rate of the reaction is constant regardless of that. Okay, it can still be influenced by temperature, and that can be reflected in the value of K. You know, the higher the K value, the higher the rate, right? Because if you look at the general form of the rate law, right, rate is equal to the rate constant K times the concentration of A to the power of N, right? And we're saying that if, in this case, right, if N is equal to 0, then this part of the equation here would evaluate to 1, and so the rate is literally just equal to K. Okay? So, like I said, K is temperature dependent, right? So like if the temperature goes up, then this value of K would go up for that reaction, right? So typically we're going to be talking about reactions at a certain temperature, right? So the problem will say, you know, at 30 degrees Celsius, or at standard temperature and pressure, right? 0 degrees Celsius, or at 100 degrees Celsius, right? Okay, so let's talk about what the units of this rate constant are in this scenario. Okay, now in class we talked about what the units of the rate are. Okay, the units for the rate of a reaction are usually moles per liter per second. It's the change in concentration per unit time. Okay, so it's moles per liters per second. This would also be the same as saying capital M per second, so molarity per second. These would be the same thing. Okay, so look at this, right? If the rate has to have these units, and the rate is simply equal to K, then that means that this rate constant K has to have those exact units. Okay? So for a 0th order reaction, and there's only one reactant, right? We're talking about a real simple reaction like this. So A decomposes into B plus C. If the reaction is 0th order with respect to A, then the units of K have to be the same units as just the rate. So these would be the units of K, moles per liter per second. Okay? Now, let's consider a slightly different scenario. Okay? Let's look at if it's first order. Okay? Let me erase a little bit of this here. Let's see. Uh-oh. How do I get back to my drawing of things? Oh no. Like I said, guys, technical difficulties. Let me try this again. Okay. All right, here we go. All right. So let's say that A is decomposing into B plus C, so same reaction as before, but now we're going to say that the reaction is first order, okay? So once again, what that means is that the concentration of A does influence the rate, okay? So at the beginning of the reaction, when the concentration of A is very high, the rate is going to be larger, right? And as A decomposes into B and C, the concentration of A is going to go down, and so the rate will decrease, okay? This would be the rate law, right? Because remember, n is this exponent, and if n equals 1, then this is it, okay? So the question is, what are the units of k, right? What are the units of the rate constant, okay? Well, the units for the rate have to be moles per liter per second, okay? Now I'm going to set up down here, I'm going to set up a sort of an analogous equation, okay? This thing, okay, the symbol for the reactant inside of brackets, this means concentration of A. Concentration is in units of molarity, or moles per liter. Okay, so A, or the concentration of A, is moles per liter. Okay, so here's the question, right? What do the units of the rate constant need to be in order to cause this reaction, or cause this equation to be an equation, right? What do the units of K need to be? The answer is, and I think I may have just made a mistake here. Oh no. How do I get back to drawing? This is so tragic. Oh, here we go. Am I good? Oh, good grief. I am hardcore struggling here. Oh no. I feel like such a Zoom noob. Am I good? Here we go. Okay, so the units of K, what do the units of K need to be? They must be inverse seconds, okay? 1/seconds. That's the thing that would need to go here, right? If it's going to be multiplied by this concentration of A, this thing is what the units would need to be, 1/seconds, so seconds in the denominator. This is what the units would need to be in order to end up with the units for the rate that we need, okay? So the units of K would be 1/seconds. This is referred to as inverse seconds. Sometimes it is represented like this, seconds to the -1. Very strange, very sort of abstract kind of concept, and yeah, it should be, okay? That doesn't really make any sense. What does that even mean? Inverse seconds, okay? It doesn't have to necessarily mean anything. It's just what the units need to be, okay, in order to make that equation work, okay? Now, I'm not going to spoil it and tell you what the units of K would need to be for n equals 2, okay? Or if n is equal to 3. I know we said that n can only be 0, 1, or 2, but actually this can occur, not exactly n equals 3. Let me be a little bit careful here. Let's say you had a reaction that looks like this, okay? A plus B makes C. Remember how I said that the rate law factors in both reactants? You could actually have the total order of the reaction be more than 2, right? So the rate law, the general form of the rate law would be this: K, and then the concentration of A to the power of n, concentration of B to the power m, right? Let's say n is equal to 1 and m is equal to 2, okay? Then the total order for the reaction would actually be 3. Right? So that's how that's talked about. That's sort of the terminology. The total order for the reaction would be third order. It's first order with respect to A, second order with respect to B. Okay? All right. This video is already encroaching on 20 minutes here, so I'm going to leave it at that. I hope that this is enough information to at least allow you to start looking at the last couple of problems from the part one of that 5.1, 5.2 problem set. I will be available for consultation during the office hours today from 1:30 to 3:30 p.m., please send me an email if you would like to utilize that. I am not posting a random Zoom link anywhere, so if you want to meet with me, let me know, and I will send you a link, okay? If you need to meet with me outside of those times, that is also probably fine. Just let me know, okay? In terms of what you're responsible for this NTI day, simply watching this video and attempting to complete part 1 of that assignment is sufficient, okay? If we are back in school on Monday, then that's it, okay? If we happen to have another NTI day on Monday, then I'll put together another video, and that second video will enable you to work on part 2 of the assignment, okay? But if we're back in school on Monday, then we'll just work on part 2 in class on Monday, okay? All right, well, that's that. Hope you guys have a nice day, and stay inside, okay? Be safe. Thanks.